No. The session will be on the feedback amplifiers. First, let's discuss a bit about them. I have one PDF. We can go through that first, and then we can go to few problems. So, let me just go through this PDF by minute. So, the feedback concept is that you can take a part of the signal at the output to the input. That is what this feedback is. And there can be different types of feedbacks we will see. And on type of amplifiers we have voltage amplifier, we have current amplifiers, transconductance, transistors amplifiers. And we will study the feedback amplifier topologies and a few characteristics of negative feedback amplifiers. So what is a feedback? Feedback is a portion of output signal. Let's say if it will be an voltage and then a part of the voltage, or current, the part of the current is taken from the output of the amplifier and is combined with the input signal. One second. And when it's combined to the input signal, it's called as a feedback. So why do we need feedback? To reduce distortion, and we should have a very small amount of factors that should affect your gain. So in nutshell, we need to sensitize our circuit. This is the basic diagram, block diagram. This is our basic block diagram of the feedback amplifier. So here we have three components. One main is my amplifier, one is sampler, one is mixer. Okay, mixer or comparator, a mix sampler, and a feedback network. And we have feedback network here. So these are the main components of the feedback amplifier. The sampler is, it takes a signal from the output through a feedback network. Feedback network may comprise of several passive elements, and then a part of it, or a fraction of the output signal, is fed to mixer, and mixer mixes the signal and it gives it to the input of the amplifier. So this is the configuration of feedback amplifier. So we have A is the gain of the feedback amplifier, gain of the amplifier without feedback. Here x naught is phi naught, and xi is the input to the amplifier without feedback, so it will be phi naught. Actually here this will be phi naught by phi I. Similarly, with feedback it will be phi naught by phi s, and this will be phi f by phi naught. So these are the three main parameters. And x here, that is xf, it will be either voltage or current. So we will see when it is voltage and when it is current. And that depends on the sampler, how we are sampling, and also mixing, how we are mixing at the input. Now, types of feedback. We have two types of feedback. We will be mainly focusing on negative feedback in the questions as well, and here in the discussion as well. So, but there are two types of feedbacks. One is positive and one is negative. If the feedback signal is in phase, what does phase mean? That if I have a signal like this and I give it a feedback signal which is again in the same phase, what will happen? It will add up, right? This will be my new signal. So this is a positive feedback, and in positive feedback we have the same phase. then the net effect of the feedback will increase the input signal given to the amplifier. That is what here I have shown. So it will increase its amplitude. This type of feedback is said to be positive or degenerative feedback. So this is how the circuit looks like. Let's say I take a part of signal, that is x naught is equal to AXI. Xi is the output of, sorry, Xi is the input signal, x naught is the output, and I take the part of it to the feedback circuit, that is Xf is beta times x naught, and now I feed it to the mixer. Now for, see here, now for positive feedback. Now for positive feedback, my input should be the source signal, that is my Xs, plus the feedback signal, that is your positive feedback. So now if I want to calculate the gain of the total circuit, that is comprising of the feedback network, I should write AF as x naught by xs, and from the first equation, that is this, I can write xs as xi minus xf. So I take the x naught in the numerator, I can write 1 divided by xi by x naught minus xf by x naught, and we lead to this equation. We can see that the denominator is always less than 1. So my gain will always be greater than A. And what is this AB called as? AB is called as a loop gain. The product of open loop gain, that is A, and a feedback factor, that is beta, is called as open loop gain. Now if AB is somehow equal to 1, then my gain can overshoot to infinity. And then we can see that the gain of the amplifier with positive feedback is infinite, and in amplifier gives output signal without any input signal. So it goes into the oscillators, and we call it as an oscillator. We don't need that. We don't want to destabilize our circuit. So what does it do if we have a positive feedback? It can increase the instability, reduce bandwidth, because the gain bandwidth is always the same. So if we increase the gain, we can decrease the bandwidth, and you have an increase in distortion and noise. We don't want that, right? So what we prefer is negative feedback. If the feedback signal is out of phase, I told here that it is in the same phase. Now what if it is opposite? Let's say I have a signal like this, and I have another signal, feedback signal like this. So what will happen? The amplitude will decrease, right? So this is a negative feedback. So it will decrease the input signal given to the amplifier. And correspondingly, the output signal is decreased. This type of feedback is said to be negative or degenerative feedback. So now if I have to reduce, so the input signal will be xs minus xf. Following the same procedure, AF can be written as x naught by xs, and then x naught by xs. Xs can be written as xi plus xf. So what does it lead us to? This equation. So from this equation we can see that the total gain of the network including feedback is always less than 1. Right? So what are the advantages? Increase in the bandwidth. We can manipulate the input and output impedance, and we have a decrease in distortion and noise. So we have a lot of advantages, and we have a disadvantage as well. That is, we have a reduced gain. So as we see here in this equation, let's call it number 2. So let's first see what are the different types of amplifiers. Then we will go to the type of feedbacks and how we can choose the different type of feedback based on the amplifier we want to design. So let's first discuss what is the voltage amplifier. This is a typical circuit of a voltage amplifier. We have voltage as the input and we take the voltage as the output. So what is desired is the source voltage Vs, it should get solely applied, or we can say the whole source voltage should get applied at the input of the amplifier, and at the output whole voltage should get applied at the load resistance, such that V0 is directly equivalent to A times Vs. So this is our goal. So voltage amplifier, for the voltage amplifier, input resistance Ri is large compared with the source resistance. So when Ri is very much large than Rs, that means from the voltage law, Vi is Ri by Ri plus Rs times Vs. When Ri is greater than Rs, so I can write Vi is equivalent to Vs. So that's what we need. Similarly, at the output, V output will be RL divided by RL plus R 0 times AVI. And if RL is very much greater than R 0, then it will be simply AVVI. And VI is Vs, then it leads us to V 0 is equal to AVS. So that's what is written here. If the external load resistance RL is large compared with the output resistance R 0 of the amplifier, then V 0 is equal to AVI and AVS. Such amplifier provides a voltage output proportional to the voltage input, and the proportionality factor does not depend on the magnitudes of the source and load resistance. Right? Hence, this amplifier is called as a voltage amplifier. And what and in the case of ideal voltage amplifier, right? For the ideal voltage amplifier, we should have an infinite input resistance and a zero output resistance. Right? If we have infinite this, I can get Vi is equal to Vs. If I have zero this, I can get whole voltage across the RL. So that is what the voltage amplifier, ideal voltage amplifier is. Now, in case of current amplifier, figure 1.2 shows the Norton equivalent circuit. See here, this is the circuit. So now, if I want my whole current to flow through the amplifier, so what will be the desired values for Ri? So what I want is Ri should be as low as possible, such that the whole current flows through it, because the current always flows through the least resistance path. And at the output, what I want is RL should be very much less than R naught. So at the input as well as at the output, I want both the resistance to be as low as possible. It's also written here is that if amplifier input R naught, Ri is 0, then II, that is current input through the amplifier, is equivalent to source current. And if the amplifier output resistance R naught tends to infinity, then IL is AI. Such amplifier provides a current output proportional to the signal current, right? And the proportionality factor is independent of the source and load resistance. This amplifier is called as current amplifier. And for the ideal case, we should have 0 Ri and infinite R naught. And for the practical cases, it should be less than Ri should be less than Rs, and R naught should be very much greater than Rl. So this is what is desired in the current amplifier. Now let's see the transconductance amplifier. You can stop the video. Oh, wait a second. It's already okay. It's already written here. So what does the transconductance mean? That means we have to take the current at the output and we have the voltage at the input. So from the first two cases, what do we infer? We infer that If we have to take current at the output, then our output should be greater than load resistance. And if we have to take the voltage at the input, as we are supplying the voltage to the input, so our input resistance should be very much greater than the source resistance. So that is what transconductor amplifier is. So for the ideal case, our input should be infinite and our not should be infinite as well. Yeah, right? So when R naught is infinite, whole current will flow through RL, and when Ri is infinite, whole voltage will be applied across Ri. Similar goes with the transistors. That is, you have to take voltage output, or you have to take voltage at the output node, and you have to supply the current at the input node. So your Ri should be ideally 0, and your RL should be very much greater than R0, or R0 should be ideally 0 as well. So these were the different types of amplifiers. So now let's discuss a bit again about the feedback networks. In the previous section, we have seen the 4 basic amplifier types, right? And their ideal characteristics. In each of one of these, we can sample the output voltage. Sample means we can take a sample either of the voltage or the current at the output by means of a suitable sampling network and apply the signal to the input through a feedback two-port network, so that will give you a beta feedback vector. And at the input of the feedback signal the feedback signal is combined with the input signal through a mixer network. So we have sampling network, we have feedback network, we have mixer network, and we have our amplifier. So this is a basic diagram. At the output of the amplifier, we have the sampling network. The signal goes through this network and then combines the mixer and is fed back to the amplifier. So this is its basic working. Just give me a second. So let's first discuss about the sampling network. There are two ways to sample the output, right? Either voltage or current. According to the sampling parameter, either voltage or current. Okay. So how is output voltage sampled? The output voltage is sampled by connecting the feedback network in the shunt across the output. See here. So when you connect your network like this in the shunt, you can get a feedback voltage, and output current is sampled by connecting the feedback network in series. So like this, as the current flows through. So this is a sampling network connection. A feedback network, as I said earlier, it consists of the passive elements. It may consist of resistors, capacitors, and inductors. Most often, it is simply a resistor configuration. It provides a reduced portion of the output as a feedback signal to the input mixing network. It is given as like this. Similarly, it will be IF times beta times, let's say, I out. While beta is the feedback factor, okay, its value lies between 0 and 1 because it's a passive network. Like sampling, there are two ways of mixing the feedback signal, right? Either you can mix it as an voltage or you can mix it as an current. So if you keep series input connection, it will be a voltage feedback, voltage connection at the input, and if you keep a shunt, it will be a current. So it's the opposite of what you do for the sampling network. So here it is shown. If it is in series, this is a source series mixer. It will mix the voltage, and this in shunt, it will mix the current. These are the advantages: stabilization of the gain, bandwidth increase, decrease, distortion, noise. We can change the input, increase the input impedance, decrease the output impedance. We will see about that. So what is stabilization of the gain? So we can, stabilization gain is somehow related to the reduced sensitivity of the circuit, right? So this is my gain with feedback circuit, negative feedback. If I differentiate it both sides with A, so I will get this equation. So if I, it should be here A, F. So this is dAF by AF is equivalent to dA by A divided by 1 by 1 plus AB. So this is here AF. dAF by AF is a fractional change in amplifier with feedback. dA is a fractional change in amplifier without feedback. So we reduce it by this term. So this is a reduction in the sensitivity. The sensitivity is defined as the ratio of the percentage change in the voltage gain with feedback to the percentage change in the without feedback. In the voltage gain without. So it gets reduced by this factor. So stability of the amplifier increase with increase in the DC. Desensitivity is 1 plus AB. The more it is, more stable the circuit is. Similarly, in terms of bandwidth, bandwidth remains same. If gain increases, bandwidth decreases, gain decreases, bandwidth increases. So if my gain, so if the gain is increased by a factor of 1 plus AB, then bandwidth will, sorry, if my gain is decreased by 1 plus AB, the bandwidth will be increased by 1 plus AB. Similarly, these are the proof terms. And similarly, let's move on. So you can do this. Similarly, decrease distortion. Similarly, as a gain, like gain is reduced, distortion reduced, noise reduces. And we have increase in the input impedance. The negative voltage feedback. So if you take a voltage at the output and feed it back to the input of the voltage amplifier, so it can increase the input impedance by this factor. So this this process can be used for the impedance matching. So this is the advantage for the voltage amplifier. We get a very increase in input impedance. Similarly, at the output, we will be required to decrease the output impedance for the voltage amplifier. That can be also done, and it gets reduced by this vector 1 plus AB. Okay, so we have these four type of topologies. That is series. Always remember that first term refers to the sampling, and second term refers to the mixing. So if we take a voltage sample, that is series voltage, and oh, wait a second. So here it is. It's otherwise written here. So series voltage means it's a mixer. It's voltage mixing at the input, that is series voltage, and shunt voltage is the sample. This is sample. This is mixed. So this is a voltage series at the input, voltage shunt at the output. Similarly, this is uh, current. mm, current shunt at the input and current series at the output. So what is this? This is a voltage series at the input, and this is the current series at the output. This is again current shunt at the input and voltage shunt at the output. So how do we name them? So here it is voltage series, sampling, mixing, and this will be, this is current shunt, sampling and mixing, sampling, mixing, sampling, mixing. So we have voltage series feedback. Just to remember what it is. First one is sampling, mixing. So you are taking voltage at the output and you are adding the voltage at the input. You're taking the voltage at the output, you are adding the current at the input. You are taking the current at the output and you are adding a voltage at the input, and you are taking the current at the output and mixing the current at the input. So these are the four types of needle feedbacks. Let's see if we, okay. Now if we check the voltage series feedback. Voltage series feedback is, take the shunt, add the shunt circuit and add the series at the input. So let's check the resistance for this circuit. So we need to calculate this ROF. Initially it was R naught. So When we calculate the output resistance, we short the input voltage, that is Vs. So let's say the test source at output as V comma I at the output. So my ROF will be V by I. Due to feedback input voltage, VF reduces the output voltage. Okay, so the current of I is flowing through this network. So my I will be voltage here, that is the test source. It will be V minus AVI, this voltage, by R naught. And this AVI, we can see that I have a feedback voltage here in series, that is Vf is equal to V times V naught. So if I keep A as the same, I have a signal of minus times VV naught here. So this is VV naught. So one second. So since I am adding the test source at V, that is equivalent to V, so I am taking V naught as V. So it will be I is equivalent to V times 1 plus A beta by R naught. And then V by I is this term, that means R naught or ROF, that is resistance output resistance of feedback, is R naught divided by 1 plus AB. That is output resistance with the feedback reduced by the factor of 1 plus AB. So that's what we need in the voltage amplifier. Similarly, for the input, we can add the test source, and if we apply KVL to this loop, then Vs is equal to Vi plus Vf. Vf is the feedback voltage, and Vi is the voltage across Ri. This will be IRI, and this is beta times V naught. So then you can again do this calculation. You'll find that the input resistance is increased by 1 plus beta times A. So it increased by 1 plus A times B. Similarly, we can do for these uh, other three amplifiers, right? So let's see first few. Let's check now few of the questions or problems on this type of circuits. So just look at this question and try once. In this question, we need the overall input current gain, overall current gain, I naught by IS. Okay, so this is the circuit. So what we can see is we are taking current at the output, sampling the current, and we have a shunt mixing as the input. So this is a current shunt amplifier, right? The values are given. We have a gain of amplifier as well, that is 160, and we have the gain of the feedback network, beta is 0.25. The values of the components of the ideal current amplifier in the feedback path. So these two values are also given. These are the ideal values, 0 and infinity. Values of the components of the non-ideal current amplifier in the feedback. Also, okay. So this is for the non-ideal case and also the ideal case. Find the value of current gain, that is I naught by Is, for an ideal feedback network. So we need to consider R in beta is 0 and R out beta is infinity. The value of the components of the ideal current amplifier in the feedback path are given. Okay, so enter the quotients. So let's start. So as I said, this is current sensing, current mixing. So at the input, this is Is, this is If. What I can write is 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 equivalent to If plus In, right? And what is my If? This is beta times Ix. If is beta times Ix. So it will be Is is equivalent to beta times Ix plus In, right? And Ix, since R and B is in 0, Ix is simply I naught. This implies Is is beta times I naught plus In. Now I naught will be AI times In. So Is will be beta times AI times In plus In. So this will be Is equal to 1 plus AIB times In. Okay, but what do we need to calculate is I naught by Is. So my In is Is divided by 1 plus AI times beta, and I output is AI times In, therefore I output will be AI divided by 1 plus AI times beta times Is. So I naught by Is will be AI divided by 1 plus AI times beta. You can substitute the values. Everything is given. 116 divided by 116 times 0.25 plus 1. So it comes out to be 3.87. Next, refer to the circuit again, the same circuit. find the value of input resistance for the current amplifier due to an ideal feedback network. The values of the components of the ideal current amplifier. And okay, let's draw the circuit. Since we have to find the input, let me just draw the input circuit. We need to find this resistance. Alright. This is IS, and I have a voltage of Vs here. So I need to find Vs by S. Vs by Is. So what do I have is Is, let's see, let me write it as I beta plus II. So this will be I beta is beta times Ix plus II. So Ix is I naught, so I can write Is as beta times I naught plus II, or Is is A beta times II plus II. So again Is is II times. What do we need to find is Vs. Vs is I times Ri. So I can write Is equivalent to 1 plus A beta. So in place of I can write Vs by Ri. So my Vs by Is is Ri divided by 1 plus AB. So Ri is my initial input resistance, and it gets divided by 1 plus AB. So the input resistance is reduced. So this is the input resistance we have to calculate for this. Now I know A value, that is 116. This is 0.25, and we have also the Ri value as well. That is 3 kilo ohm. So you can substitute the values and get the answer. give it a try. We need to find the output resistance. First, let's draw the equivalent circuit. Draw the equivalent circuit once and then try to solve it. Okay, let's draw the equivalent circuit. Okay, so we have this A times IN, and we have a feedback with zero resistance. So this is my I naught. I need to find this resistance. And this is R out. So what we need to do is we need to open the current source at the input. This is II, and this will be my beta times Ix. Okay, so this was my I beta. So now let's go for the calculations. Let's say this is the voltage V naught. So your I naught is V naught by R naught plus A. So this is AI times I input. That is this. Also, I have I input plus I beta, that is I feedback 0. This implies I input is equivalent to I beta, that is minus beta times IF, that is minus beta times I naught. So I input is minus beta times I naught. So my I naught plus sorry, that minus this beta then we move it on the left hand side, and then 1 plus AI times beta is equal to mu over r. So this implies V naught plus I naught is R out times 1 plus right. So for the current amplified case, what happens is the output resistance increases. So this is a advantage of the feedback amplifier. So when it increases, more current now will flow through the load resistance and we will get a desired output. So now again we have the similar questions, but now we need to include the non-ideality. In the previous we treated them as the ideal. Okay, so IS again is I beta plus IN. So this will be, let's say this is the voltage of VS here. It will be I beta, that is beta times. Okay, 1 second. Now I beta is Vs by R out V plus beta times Ix, right? And since Is is IB plus IN, so it will be Vs by R out V plus beta times Ix plus IN. So now Ix is not directly equivalent to I or I naught because of R in underscore beta. So it will be a current distribution. And so it will be a current distribution between R naught and R in underscore B beta. So it will be current distribution between R in underscore beta and R out. So my Ix will be R out divided by R out plus R in underscore beta So it comes out to be 0.96 times I naught. So now I substitute it here. So my Ix is Vs by R. I naught is Ai times I in. So it will be I in will be common. So we 1 plus Ai times B multiplied by 0.96. Right? Also, Vs is the input voltage. It is I in times R in. You can see from the figure, Vs is this voltage. That is I in times R in. So you can write Is as I in times R in R out B plus I in times 1 plus 0.96 AI beta. Okay, so Is, if I take I in as common, so this is R in by R out beta plus 1 plus A times beta 1 plus 0.96 beta. This means I in is Is times R out underscore B divided by R in plus R out underscore B 1 plus 0.96 AI times beta. Since Vs is R in I in, therefore we can write Vs as R in R out B divided by R in plus R out underscore B 1 plus 0.96 AI underscore beta multiplied by Is. Now R in dash, that's the total input resistance, will be Vs by Is. So that is basically. Substitute all the values, there are all the values, you can get the answer. Right? Answer comes out to be 99. Okay. Um, try it, you can try it this yourself. So our output for this case will be our input B plus our output times 1 plus AI beta dash. Beta dash, I have written beta dash, so this may have some other, like we had previously 0.96, there can be some terms, underlying terms as well, so you can accompany them in beta dash. But try this, and if you have any questions, then you can just directly mail or submit it in the form or in the comment section. I guess we can stop it here. Not feeling well. We discussed on the feedback amplifiers, and we will have a last session tomorrow. I guess that's it. See you.